welcome to the lessons from integrating the Oculus Rift into Unreal Engine 4. My name is Nick Whiting. I'm the lead of VR and visual scripting at Epic on UE4, and this is Nick Donaldson. Introduce yourself.
I'm a designer, artist, anything technical that isn't programming.
And basically all those cool, sexy visuals you saw in all the demos, this guy right here, super talented.
And one other guy.
Yeah, I'm one other dude. So small team, but we're a scrappy bunch. So it helps. Also, I should give a shout out to Art back there from Oculus. He's the man. He helps us immensely.
He's a total
everybody,
mofo.
Round of applause for Art. Without him, this would not be possible. So anyway, I'll get right into it since we don't have a whole lot of time left. So the talk today is going to be kind of broken up into 3 parts. We're going to kind of talk about the technical learnings that we did while integrating the engine, and we're not going to go super deep. We just think it's useful for people to have an understanding of how things work under the hood as they're building stuff on top of the system. So I'll kind of give a quick overview of that. Then I'm going to turn it over to the other Nick, and he's going to talk about how we optimized the showdown demo that you guys can see on the Crescent Bay prototype to run at 90 hertz and the high resolutions that are required, because it's no small feat. It's a bit of an art form, so we thought we would give you guys a post-mortem on how we did that.
Creative problem solving and optimization.
Indeed. So in the final bit of the demo, we're just going to go over a couple of the learnings that we had from making all these demos with Oculus through the years, because one of the things we really value about the VR community is how open everybody is. We know we don't just share our successes, we also share our failures in hopes that others can kind of pick up the ball and run from where we left off. So without further ado, let's get to it. So Epic and Oculus have a long history together. We knew the Oculus guys before they were Oculus. So we were fortunate enough to kind of have access to a lot of the early prototypes and kind of went along for the ride with them. The first real prototype that we did was with their HD prototype at E3 2013 last year. We basically just took one of our tech demos called Elemental that we used to premiere Unreal Engine 4 and made it into a walkable experience. And fortunately, Oculus that year actually won the Game Critics Award for the best hardware up against the PS4 and 360, and so that actually got us a lot of internal momentum at Epic that, hey, this is a real thing. The next one we did was at the beginning of this year, in January, when Oculus came out with the Crystal Cove prototype, and we combined 2 different demos that we had, the Elemental demo and our strategy game Tower Defense demo, into one demo that kind of showed off the positional tracking. And again, Oculus won Best of Show there, so that was kind of further adding ammo to our internal support of VR. And then GDC this year, with the premiere of the DK2, we created Couch Nights, which is kind of our most ambitious demo, where we actually started adding gameplay and a shared social experience, and used the HMD tracking to map your movements onto avatars within the game. And we're fortunate enough to once again be able to premiere a couple demos on the Crescent Bay prototype, the Showdown demo, which is kind of a mashup of our Infiltrator demo and the Samaritan demo, to create a high-end visual kind of cinematic experience to see how far we could push the visuals while still maintaining the 90 hertz refresh rate. So with that, I'm going to go into the engine integration overview, and there's kind of 2 main components of that. In order to get the Rift working with UE4, the first thing we had to attack was the rendering modifications that were needed in order to do that. So we had to make things render in stereoscopic so we could have 3D, and we had to do the distortion pass. And then the second thing we had to do was account for the latency. I'm trying to reduce that so that the motion of your HMD actually matched up with the visuals in the game. So we'll start with the stereoscopic rendering. So everybody's familiar with games that you project onto a 2D screen and you get the illusion of depth, but there's not actually a whole lot of depth information for real there. So if you imagine how we render games traditionally with one camera, it's kind of like if a human had one eye. You've got the Cyclops vision. You can tell hints that there's depth there because of the shadowing and the visual information, but you don't really get the sense of real true depth in the 3D. And that's because humans are blessed with 2 eyes that are separated by this thing we call the interpupillary distance, or the IPD.
That's not an actual thing. It's just we call it that.
Yeah, it is the name of the measurement. Anyway, bastard. On most people, on average, it's about 6.4 centimeters, but it can go into the 5 centimeters, or if you're like Uma Thurman, it can go up to the several meters range. But the difference between the images and the 2 eyes is really kind of what gives us our sense of depth. So rendering in UE4 went from the single image that you see on the left to a double image that you see on the right. And that's a pretty complicated scene, but if you simplify it into a diagram where you have one black dot, which is the object you're trying to render, you can see the difference between the 2 on there. In the traditional rendering on the left, you have one dot that's centered nicely in the screen, but when we go to stereoscopic rendering, we have to move the camera to the left and to the right to capture two different images, just like we have two different eyes. And you'll notice that the same dot in the center actually renders in two different positions on each of the screens. You can kind of see the same effect too if you look off into the distance and hold your finger up. As long as you keep focused on the distance, your finger, you'll actually see a double image, and that's kind of the same sort of effect that you see here. So in order to adapt Unreal, we took the camera location that we already had from making all the games we do with Unreal Engine, and then we had to move it to the left and to the right by half of that IPD distance. So a pretty simple calculation, but the one thing to note here is that we have to convert from real-world units, your actual IPD, which is about 6.4 centimeters, to Unreal units. And to do that, there's a scale in every level that's your world to meter scale, and that basically tells you how many Unreal units there are in every meter in the real world, and that's what we use to go between the two. And we don't only use this for the interpupillary distance, but with positional tracking, when you're moving your head around, like that same motion is scaled by the same factor, so that the distance between your eyes is always scaled to the distance that your head is actually moving. And it's actually very important to keep those two the same scale, because if you don't, you start feeling really, really weird. But the cool thing is, you can actually tweak that scale to make yourself feel like a giant or feel like a little midget, so you can actually change it and get some cool effects out of that. So the easiest approach and how we kind of approached implementing stereo rendering at a technical level is to just repeat the draw calls for each eye. So basically when we batch up all the stuff for the rendering, we say, hey, here's the left eye perspective, send all the draw calls for all the meshes and stuff in the screen. And then we're like, hey, here's the right eye stuff, and we send that same batch of draw calls over there. So that doubles the number of draw calls, but it's super simple to implement, and it's compatible with all of our current rendering effects stuff. So we opted to do that first because it was the easiest and the most compatible. And we wanted, since people were building a lot of different things on top of the engine, we wanted the most kind of straightforward experience. But we were able to optimize that a little bit because for certain post-process effects and other effects, so occlusion queries and eye adaptation, we reuse the data from the left eye in the right eye, so that we don't have to compute those things twice, and that saves us a bit of time on there. A better approach, which we're actually looking at doing in the future, is to do double rendering in the shader. So basically take the load off the CPU, and then in the shader, draw each image twice for the stereoscopic positions. So we're looking at doing this, and it moves the work onto the GPU, but it's much more invasive to the render pipeline. But we're looking at this as a future optimization because with things like the Samsung Gear VR, draw calls are becoming much, much more important, and paying the 2x cost isn't really ideal in a lot of situations. So that's stereo rendering. So we're going to go over distortion really quick. And fortunately, the SDK does this for you now, so you don't have to worry about it. But there's one result from this that is very useful when you're actually developing content. So I thought I would give a quick overview of this so you guys can understand what's going on a little bit better. So if you were to look at like a normal regular grid that was square through the optics of the Rift, it would actually look a little bit like this, because the optics in the Rift try to stretch the image so you have a wider FOV. But unfortunately for us, that means we can't just throw the images up on the screen and have them look correct in the eye. So what we need to do is use basically the anti-filter to this to kind of undistort the actual image that we render to the screen, so that when you look at it through the distorted optics, it actually looks correct. So if you look at this diagram, basically we render like it does on the top left, and then the optics from the Rift make the image look on the top right. But when you combine the two of them, you get an undistorted image that looks correct. And like I said, you don't have to worry about this at all because the SDK does it for you. But by virtue of the process of doing this distortion, you actually shrink the image a little bit. So, back up real quick. If you notice on the outskirts of the image here, there's this kind of black dead area, and that's because we kind of pull the image in as we scale it. And by virtue of doing that, you're losing a bit of the resolution. So one of the things we do is have a screen percentage where you can scale up the back buffer that we use to render the image, so that when we lose the resolution to the shrinking, you don't notice as much of the effect. So the white box there is the actual device resolution. So for the DK2, 1920 by 1080, but we actually render to a back buffer that's somewhere between 130 to 150 times, or not 150% of the size of the original back buffer. If it was 150 times, we'd be really hosed. But that makes it so that the lost resolution is kind of outside the final bounds of the render target. So the screen percentage is one of the things that you're probably going to be tuning quite a bit as you're going through and developing content in order to get things to the frame rate.
Usually making it lower and lower and lower and lower.
Sadly so. But the values in Unreal Engine can range from 30% to 300%. So 30% means you're using a tiny render target and scaling up, which saves you a lot of performance, but you sacrifice visual quality. Or you can go up to 300%, which if you have a really beefy GPU, gives you a beautiful image, but the perf is obviously much higher. And all the devices that Oculus have recommended percentages, but you can override a bit to add scalability if you're willing to make those kind of visual trade-offs. In-game, if you're tweaking it, there's a useful command that some people don't know. If you type HMD SP and then a number, that resets the screen percentage. So 100 is 100% of the back buffer, and anything over 100 means that you're rendering to a larger target and scaling down so it will look better. And not only is this important for just kind of the visual quality of it, if you're going to use temporal AA, which is what we do for most of our demos because it's a lot faster for us, temporal AA actually has better results with the higher resolution because when you jitter a lower resolution image, you kind of pay the cost of the low resolution image and then jittered, and it kind of magnifies that. So it's important to, as much as possible, use the highest screen percentage that you can and still run at frame rate. So now that we covered rendering, we're going to talk a little bit about reading the sensor. So when we first did this, when we first hooked it up, I'm like, okay, we have a new input device, basically. I'm just going to pull the HMD sensor at the same time where we read controller input and everything. And so I hooked it up, and it worked, and everything was awesome. And I put it on. I'm like, hey, it's pretty awesome. You can look around and see the world, and it's really cool. And then I started showing it to other people who had actually had good VR experiences with it, as opposed to my very nubile experiences with it. And they were like, nope. And so everybody said, your motion to photons latency is too damn high. And so we had to work on that the guys at Oculus actually put it through a latency sensor, and we were up above 50 milliseconds of latency. And if you've heard Abrash and Carmack talk, that's well above the red line. That's actually multiples above the red line. So we needed a couple different approaches to cut this down. So the first thing was that we found out the video card was actually buffering a few frames. And what that meant was by the time we read this sensor, it had already put some frames in the queue, and we needed to actually flush those in order to reduce the latency so that it wasn't building up frames as we were actually moving our heads around. So we added the r.finish current frame, which forces the video card to flush the current frame that you're on before moving on to the next. So that's done at the engine level for you, and you don't need to worry about it. But the key understanding here is that that actually trades a little bit of performance for the latency reduction. In general, we like to make that trade-off because latency reduction really is key to developing presence. But the good news is that with the direct mode in the 040 runtimes, you don't have to worry about that anymore, and we don't have to actually use the finished current frame, which is awesome. So the second thing we started looking at was that we were sampling once per frame, and that led to a lot of latency. So what if we wanted to sample multiple times per the frame to try to reduce the time from our last sensor read to when the actual image was presented? So we have a simplified version of our render frame here. It's not actually this simple, and we're assuming 60 hertz, and I rounded to 17. I know it's 16.66, all that crap, but for the sake of math, we decided to make this frame represents one 17 millisecond frame, so you're running at 60 hertz. So our first attempt, when we read it at the beginning of the game frame, our latency that was engine-induced, not counting all the driver cards and the actual device latency, but the stuff that we could control in the engine itself, was 17, which is the end of the frame, minus the 1 second. So we had 16 milliseconds of hypothetical latency here, and that's kind of terrible. So we thought we could do better. So Oculus had the suggestion that, what if we sampled right before we sent all the image data, or the rendering data to the card? We could, in essence, basically hide the latency of the game thread. So we read once at the beginning where we read all the input, and we do our gameplay logic there. But then right again before we send all the render data to the video card, we read it again so that we can update the view position for the latest, basically after the game is read. So if you started the game thread here and you moved a little bit by the time all the game thread calculations were done, we wanted to reflect this new position. And when you do that, if you assume in our, again, hypothetical model that you do that at 5 milliseconds, the latency is 17 milliseconds minus 5, which is 12 milliseconds. So awesome, we shaved another few milliseconds off. So basically, the first sample lets us do the gameplay logic, like you can tell what you're looking at, tell what you're shooting at, but we can still update the view matrix before we send the data to the card to get a more recent and accurate view matrix to send to the renderer. So we've hidden the cost of the game thread effectively, but that means there's still a whole lot of draw and GPU time in there, how do we try to mask that? And the answer is, let's do the time warp. And I'm sure you guys have all heard of it, but it's the technique that basically allows us to hide the rest of that, or much of the rest of that latency in the frame by taking the image that we get back from the card and the renderer and adjusting it one more time based on a more recent sensor read. So I'll go over super quick how this works. Again, it's not super technical, but basically, if you have the rendered image that comes back from the GPU, we have the screen that we present to the device, but there's also a depth buffer which tells us how deep every pixel is on the screen. And if we know the XY position of the screen and the Z position of the screen, we can reconstruct where that pixel is in 3D space. So once we have the 3D positions for the image, we can actually update the rotation of the image and rotate it around you. So if this was the screen in front of you and you're looking around, basically what you're doing is updating the rotation of the screen as you rotate your head. And it's a little weird to picture, so we have a video, which will hopefully play, yes, of time warping in action. So once this plays, basically this is a static scene, and then I'm going to rotate the HMD device, and you can see how the screen is recalculating based on the rotation of the device, but we're not using any more rendering data as we do this. It works left and right, and then up and down. There we go. It's very hard to capture video and rotate in HMD at the same time. It's like patting your head and rubbing your tummy. So basically, what that allows us to do is rotate the final image based on the sensors right before we present. But as you noticed in the screen, as you rotate farther and farther, there's only a finite amount of image data there. So the key to time warping is that it only works over very, very short intervals because you can only move your head so fast as we go. But fortunately, because we have to run at 75 to 90 hertz, that's not really a huge issue for us because the amount that you're moving your head in that time isn't gigantic, and the technique actually works pretty well. So again, in our simplified version of the frame, and there's a typo at the bottom, but if we do the sampling again right after all the GPU stuff is done, right before the present, at say 14 milliseconds, our latency introduced by the engine goes from 17 minus, should be a 14, and get down to about 3 milliseconds of perceived latency. So that's kind of how time warping works. And we've hidden much of the latency of our frame, so we have a nice low latency experience now that doesn't make people fall over and vomit. But we need to make sure that we can actually maintain the frame rate, and the key to that is people like Nick Donaldson that can optimize the hell out of the demos that we make. So with that, I'm going to turn it over to him, and he can show you the dark magic. Hey.
Hey guys, I'm Nick Donaldson, and as I said, I'm the content dude. So how do we advance this? Cool. So in working on this demo, we basically had to start with what we're making. The previous demos were the Strategy VR one, which was kind of an experiment in scale. We got our previous demo with a huge cave around you, and then I literally got the entire different project, the strategy kind of tower defense game. I attached the whole level to a note actor and scaled it down to 0.04, put it in the middle of the room, and we're like, yes. Then we had the Versus VR, which was an experiment in social kind of interaction. One of the best moments that Nick's going to be talking about later was the, yo, what's up? And being able to see each other do that is pretty amazing. So this time around, Oculus wanted something a little more kind of cinematic, a little more epic, so to speak. So we were going explosions, and we were just going for pure visual impact, basically. So we decided, how are we going to do this? What are we going to make? All we knew to start with is that for high visual impact on stereoscopic vision, near-field stuff looks amazing. Like when you've got particles flying at you, you're just like, whoa, whoa. You're just like, it's really cool. So when in doubt, blow shit up. I mean, why not? We knew that we had to draw from some existing content that we already had. There were only going to be a couple of people working on it. So we had these assets from the Infiltrator demo. We had this robot that came up, and there's sparks, explosions, all sorts of effects, guns, soldiers, and that's pretty much everything you need to make an action sequence. We also had this really cool environment from the Samaritan demo. It was a lot of believable things around you, a lot of things that were set to the right scale. So the idea was that the robot from the other demo would crash down in front of you and be this big hole in the ground, and he'd come up and, in Stormtrooper style, would start shooting at you and miss every fucking time. And despite our obvious plot holes, we thought this was a pretty cool idea. It got pointed out to us by every person who even heard it. So, but then we thought, we only have about 5 weeks to make this content before we have to start optimizing and locking things down. And we had 2 people working on the content. It was me and another guy whose lead I hadn't actually told that I was going to use him yet. So it was questionable. We also had an audio guy that we locked down later, Joey, who did an amazing job on all of that. There's technical limitations where we knew we had to run at 90 hertz with this new device, and we didn't really know what else we were going to find out about the device. So it was kind of a little bit of a question. How were we going to make this thing run at 90 hertz with crazy shit happening, explosions, overdraw? We were pretty much crazy. Couch Nights was barely running at 75 hertz. We didn't use temporal AA, which is much more expensive than FXAA, but it looks much better. There were only 2 bro dudes in the scene, 2 characters that you control, and a really kind of simple environment. And then the Strategy VR demo was actually downsampled. We had to keep turning the screen percentage down and down and down and down. And I kind of ran out of things to turn off since we pretty much just stole the highest end content that our company had ever put out, and we tried to put it into this fastest rendering experience that we'd ever had. It didn't really work very well, so we knew we'd have to make some trade-offs. We have to rip the Band-Aid off really early. So just the first one we made was light maps only. We can use Lightmass, which does an amazing job of having really nice looking offline GI. There's the indirect lighting cache, which looks pretty good these days for indirect lighting on dynamic objects. And I'd have to do fake blob shadows for pretty much everything else. When we made the first playable demo and we started having people shooting guns, we had explosions going off, we knew there just wasn't enough impact. So we actually had to add some dynamic lights to the scene, which surprisingly held up pretty well, and they didn't cost too much as long as we were being really strict with them. We had to use them for limited things. We had to have no shadows whatsoever, and we had to aggressively attenuate the radius and make sure there were not too many of them. We also had a super aggressive limit on draw calls, thanks to this guy. Fortunately, later on, hopefully we get this performance optimizations later on with the render thread, but we had to really keep the scene to under 1,000, which meant less than 500 draw calls in this whole scene.
Just draw better art, we wouldn't have to render as much of it.
Yeah, exactly. So we decided, let's design around the problems that we have, We decided to make the game slow motion because we had this kind of small cache of animations that we could pull from our previous demos. And those demos were made shot by shot which no shot lasted more than 2 seconds at a time. So every animation was between 3 and 6 seconds in length. Fortunately, we slowed the whole demo down to the point where 6 seconds of animation lasted for almost 2 minutes. Win! Like I said, creative problem solving. You had all of these other windfalls, like slow-mo explosions. Bullet time, who Kim Libreri here thought was very familiar when he did it, since he invented it. More explosions, I think I doubled up this slide. I'm just going to say it. Stereoscopic vision ruins things. Normal maps look like wallpaper. They don't look the same as they used to. There's this whole visual language of graphics rendering stuff that we've kind of used over the last few years that kind of no longer work. So we have to build things out of real geometry. There are some things that do work really well, as like a bump offset actually works surprisingly well since it works per eye. And the reflection environments look great since that's calculated per eye. The one caveat to normal maps looking like crap is that they actually interact really well with the reflection environment. If you look at how many people have seen the demo? Awesome. If you looked at the road and saw the puddles and went, ooh, that's because the normal maps actually work surprisingly well in conjunction with the reflection environment, but not so much for lighting information. In the demo, we're also stuck with a whole bunch of old content since we stole it from all over the place. The ironic part of that is that we figured we'd save a lot of time, but we actually had to touch almost every single part of the content to make it work well in VR. So there's this kind of ugly mirror of truth that happens with stereoscopic vision, is that things tend to look exactly what they are. So sprite particles look like sprite particles. They only hold up really well on very small objects because the parallax doesn't really have an opportunity to kind of expose the lies. It also works very well on perfectly spherical things, for all of the perfectly spherical things that you like to render in all of your games. Flipbook explosions also look exactly like flipbook explosions. We ended up putting the first try for making an explosion was a billboard sprite animation. And we put it into the editor, and we thought it looked great. And then we put it on and went, that's really shit. So we ended up using real geometry for that. We used a highly tessellated sphere with a world space noise function to do the kind of world position offset. And then we actually fed that same data into a black body pixel shader, which did a surprisingly convincing job. I'm pretty happy with it. Unfortunately, I'm a hack and a terrible person, so I think a real effects artist could probably do a really good job with this to make some pretty convincing results. Thick smoke is also a really difficult problem to have as well. We used a very similar trick. We actually used, in UE4, we have these spline meshes, and we use a super tessellated sausage tube kind of going through the level, and we tessellated it. So we offset kind of the position of the vertices with a very similar technique to earlier. But then, there's the ugly mirror of truth that stereo vision has again, where highly tessellated meshes look like highly tessellated meshes. And so we just had this big sausage smoke trail kind of moving through the level. So we ended up using some material tricks to work through that. Like I said earlier, the bump offset stuff works really well. And so we had this kind of second layer in there. So it didn't just look like a single surface. It was a really nice kind of depth to what we were doing there. And that worked really well. One of the other things was this dither temporal AA node that we have. Some of our tech artists came up with it last year. It basically exploits temporal AA. If you don't know how temporal AA works, it kind of jitters the whole camera. And so and then it accumulates the result over multiple frames. And we use that for anti-aliasing. But one of the cool side effects is that if you use something like this, it exploits it in the way that in the material, it kind of jitters this masked material as well. And so it kind of smooths out the result. And if you look at the previous slide, it actually gets something that looks completely transparent, which is kind of cool. It also avoids the self-sorting issues you get with transparent meshes. Like on the back faces, you often see this kind of strange tearing coming through. And it looks too legit to quit. Fake shadows and lighting. I made what I call these dynamic blob shadows on the characters' feet. And I attached these to the foot bones of the characters. And then with a vertex shader, I keep the actual height of the mesh at exactly the same height on the ground plane. And so when the characters are running along, they kind of just stay exactly under the feet the whole time. And you do some math in the vertex shader that actually figures out the height of the foot and fades and shrinks the mesh accordingly. And it works surprisingly well. One of our graphics programmers, Timothy, said, I don't think we've ever shipped a game with shadows that look good. And I was pretty proud of that. Can we play that on the video? Hacks. But it sold it, and it ran really, really fucking fast. So I was pretty happy about it. Cool. And this is the material. There's a decent amount of math going on in the vertex shader, but virtually nothing in the pixel shader, so it was dirty cheap, which is cool. For the car shadow, we had to get a little more complicated. The dynamic car came over the curb on the left, so we couldn't really just use a card. That was my first attempt, was to use a regular card, but this is the stereo problems again, where flat floating card looks like a flat floating card. So I had to get a little bit more in depth with that. So we used the depth buffer to project this AO map that we baked in 3ds Max and world space onto the ground, and then actually aligned it to did a local transform on it to the mesh of the thing. It looks pretty cool, I have to say. It was only 30 instructions, so I think I'm going to quit and reapply as a graphics programmer. Bullet holes. I stole a trick from one of our technical artists at Epic, Ryan Brox. He made this multi-bump offset parallax trick. It may be the only effect I've ever seen that is less artifacty in stereo vision than it is in regular. It had a super high pixel shader cost, but a really small screen space, so you didn't actually pay a lot for them, which is pretty cool. So now that we came up with some of these kind of creative tricks to make the game look right, we had to make sure it ran right as well, where profiling is the first step to making that happen. So profiling with real-time stats. First, we need to find out what our frame time is. So stat FPS and stat unit is a great way to start. We started profiling on our first playable thing. We threw all of our content in. we put it on our faces and we went, oh shit, it runs at 30 frames per second. So the first thing we did was run stat scene rendering, where we found out that static list drawing was costing almost 12 milliseconds. The render view family was 25, and we were just kind of in over our heads. But we can start to track down what is causing this problem. So mesh draw calls, 2,500. That's not a small amount. Let's write it down. So the next thing was to find out if we turned off the static meshes, whether we'd get that timing back. So show static meshes is a great way. The show commands are a great way to toggle things on and off. And so 8 milliseconds of static mesh drawing, that's pretty much what we saw before. Write down, move on. Stat particles. Particles are always a nice resource hog. So let's find out exactly what's going on there. And there's almost 9 milliseconds of particles there as well. Show particles is exactly the same thing. Take the next step, toggle them on, toggle them off. And we see that there's 8 milliseconds in particles. That's exactly what our stats told us before. But the most important thing to see here is that the delta between the draw thread and the GPU is actually exactly the same, even though we saved 8 milliseconds. So that means we're render thread bound. So that's what we need to be working on for now, etc. If you type show into the console, it'll just dump out a list of all the things that you can toggle on and off. And that's a great way of quickly finding out exactly where your performance is going. CPU profiling tool. This is a gem. It's awesome, and no one really knows about it. It's kind of hidden in the menu somewhere. But what it lets you do is capture a preview of the scene, and then you can actually find out down to the draw call level exactly what's costing you what. So here's a quick profile of the render thread. We can see the static list drawing, 6 milliseconds. That matches up exactly with the stats that we saw before. There is a transparency you can see in that category. You can actually see exactly which particle effect is costing us 3.5 milliseconds almost. And then there are other things like HCB occlusion, which is something I turn off the second I open a project. I'm sure we'll improve that at some point. Profiling the game thread is really important as well, because as Nick was saying, it goes game thread, render thread, GPU. And if you have a fat game thread, then you're kind of messed up from the beginning. So in that same early content that we had here, here's the game thread that we have. And you can see there's one thing that's costing us 3.5 milliseconds, it looks like. And the great thing is, it tells you exactly as before, it tells you exactly which asset's causing it. And then if you mouse over that little tag thing there, it'll tell you exactly what's going on with that function call. And it's updating 2,600 times. And so this was some effect that we'd stolen from Infiltrator, and it was a skeletal mesh with an explosion sim on it. And every single chunk had a bone, and every bone had a collision hull on it, and every single one of those was updating every frame. Delete. Gone. One of the easiest things to optimize on the game thread is updating overlaps and blueprint function calls, because they have a really high virtual machine cost, if I'm saying that right.
Yes.
There you go. Perf check 2.0. So we did a bunch of perf optimizations. I took all of the low-hanging fruit that I could find, and I looked at it again. So it looks like we're at almost half the frame time here, which is great. But you can see that draw thread and GPU are still really close, which is looking like we are render thread bound still. There's this kind of cool trick that I use where if you pause and then unpause, just the button on the keyboard, everything that ticks stops updating when you pause. And so the game thread usually goes away, and then the draw thread drops by a couple of milliseconds. And if you see the GPU have the same delta drop as either of those two, it means you're still CPU bound, and there's still more work to do. We're going to need a bigger boat. So on our workstations at work, we have these serious GPUs, but we also, that NVIDIA kind of usually supply for us. But these Xeon CPUs that we have like 10 billion cores on them, but they're really slow, which is great for like a light mass rebuild and stability and stuff like that. But for something like this, where we actually need a few cores that run really fast, we needed a consumer level processor. So throwing it onto one of those there, you can see we have now 4 milliseconds. Oh. It drops down to 4 milliseconds on the draw thread, which is fantastic. If you want to find out exactly if you're having problems on draw or GPU, you can just put your screen percentage to like a really low number, and you can make sure that you're draw thread bound to get a good timings on there. So the last thing is GPU profiling. If you type in, I forgot to actually write it here, it's called profile GPU, or I think it's Control-Shift, or some obscure combination like that. No wonder nobody knows this stuff. You get this awesome GPU profiler, which gives you a really nice visual indicator of exactly where your time's going. So you can see here that this bar that I have this beautifully drawn arrow to is the HZB occlusion that we were talking about earlier. It's 5 milliseconds on the GPU, which is pretty heavy. So the cool thing is, let's turn it off. There's some commands for that we'll provide hopefully later in the slides. And then if we turn that off and we run the profiler again, we have a lot of that time back, and now we can look at the base pass, which is the red bar in this one. And if you start clicking on it, it actually breaks it down to a lot of smaller categories there. The one I've highlighted there is the static opaque light mapped, which is pretty much everything in your scene. Static opaque non-light mapped is usually your sky dome, and then you can kind of start inferring the rest of the things. It'd be really nice if we had a slightly more in-depth tool than this, but it gives you a really good start on where to start looking for things. You might have to infer where some of the exact cost is going, but it gives you a really great start. So long story short is you will need to make trade-offs. You're going to have to make them early. You're going to have to make them pretty aggressively. You have to be aggressive about the changes that you're making. You have to, if you have a suspicion that there are too many objects in the scene, delete half of them and profile it again. Run something through Pro Optimizer even if it looks like shit. Just make some really drastic changes and see if it actually works. Never make assumptions. Get creative. If you're making big trade-offs, you have to make creative changes to account for those terrible trade-offs that you just made. Get technical. If you're not technical, you're not going to make this stuff run properly and look good at the same time. If you don't have someone technical on your team, then that has to be you. Learn the numbers, crunch them, just dig into it, and it's not that hard. The people on Answer Hub who are answering the questions are the people who wrote the code, and we're always answering questions on there, so it's a good place to go. Some cool things during this demo is that we got the multi-threaded renderer up and running, and hopefully that'll be in an update coming soon at some point. It already saved us multiple milliseconds here. I kept telling Timothy that I was going to turn off temporal AA because it was too slow and it was too blurry. So he made it 20% faster and less blurry. Yay! That's always exciting stuff. And now, a bunch of settings that you guys can get in the slides later that will make your things faster.
We're going to put these up on the forums too, so you don't have to actually take a photo of those. You can just download it.
Back to Nick. Thanks, guys.
All right, so we've kind of seen the technical and the optimization side. We wanted to touch a little bit on kind of the gameplay and design learnings because, as Nick said, VR is all about kind of designing around the constraints, and in that way it's very challenging and it's also very fun. But since we also got a late start because of technical difficulties, I'm going to really blast through this. So I'm going to talk like the Micro Machines man, and if you really want to go any more deep with this, you can download the slides and check it out. So the first demo, as we said, was Elemental VR, and that was kind of our baby toddler steps into there. We have a cool environment. Let's just go around because we think the environment will be cool enough that it will be compelling in and of itself. So we threw our gameplay guy in there, and he's running at like 30 miles an hour, and people are like, this sucks. I'm getting sick. So the first kind of, facepalm lesson we did was like, we have to slow down the movement. And we thought, maybe half would be a good start, but that was still, you felt like Usain Bolt running around the level. So we ended up cutting it down to about a third of normal, and that's where we found people were actually, pretty comfortable and can look around and enjoy the experience. The second thing that we noticed was there's a staircase in the level that kind of went from bottom to top. And at the beginning, because of the eye adaptation, the top of the staircase was really dark. So people just kind of looked straight ahead as they were going up the staircase, and it felt like they were kind of raising up spontaneously. And people felt, that pit in the stomach feeling like when you're going over the roller coaster, and that wasn't very good. But we found out that by tweaking the kind of lighting in the scene and the eye adaptation, we gave a very kind of bright target for people to look at so that they were looking in the direction of the motion that they were going to do, and that kind of alleviated that effect. We actually found that the Oculus guys, when they were demoing this at E3, turned on a cheat command and flew up to the top of the volcano and decided that, hey, it'd be really cool if you could ski down a volcano, and that actually became the coolest part of the demo. It was something that we completely did not intend, and they didn't tell us they were going to do it until after they showed it to everybody. So some artists were shitting bricks about it because the place wasn't kind of looking very cool, but people had a lot of fun going lava skiing. Visuals, this one's really brief because it doesn't apply as much now, but with the DK1, since the screen resolution was so low, clean lines and very kind of, low visual frequency visuals didn't look very good on the screen because you didn't have enough pixel resolution to reproduce those. So by purely chancing into it, the content that we picked had a lot of, uneven edges and a lot of high frequency textures that really helped break up the scene, and you didn't notice the aliasing quite as much as you would if you had a very clean line demo with low visual frequency. The next thing is there were snowflakes, because this castle was kind of had its roof caved in, so you could walk forward and all of a sudden you're in this kind of field of snowflakes. And that was really cool for a few reasons. The first was that everybody always went in and started looking up and sticking their tongue out, which was hilarious until we figured out what they were actually doing. They were trying to catch snowflakes on their tongue. So, I mean, that speaks to the power of VR, even at the DK1 or the HD prototype level. But the other great thing about these fields was that because you were in kind of a volume of these particles, there was a lot of near field and parallax. So when you turned around, you can see all the stuff moving around you, and it really grounded you in the experience because you could feel the motion of your head mapping up with the motion in the game. And it was really, really a compelling experience. And then the last thing that was just kind of a last-minute addition was what we call the Drunken Magic Missile. And basically what this was a little ball of GPU particles that you'd shoot off, and it would start bouncing around the scene, kind of like, you know, one of those rubber bouncy super balls that you throw and they bounce all around. And the cool thing about this was, I mean, A, it looked cool, but B, most people when they put on the Rift for the first time, you know, we're gamers, we're trained to look at a screen that's a few meters in front of us, so they just put it on and they sit perfectly still and use the controller looking around, and we're like, move your damn head, guys. So by virtue of having this super pretty thing to look around at, when they fired it, they're like, oh, that's cool, and, you know, started looking around, and without even realizing it, we were kind of training them to be better VR users by looking around, because once they started doing that, they started realizing they could look around, and, you know, it suddenly became much more interesting. And spatialized audio actually really helped quite a bit with this. The initial effect wasn't spatialized because the artist that put it in didn't know how to spatialize things, and so at the last minute, we changed it from sounding like a buzz saw that was just constantly in your ears to actually a buzz saw that was flying around the level, which is much cooler. The next up was the strategy VR, and again, this was kind of a study in contrasting scales because Palmer and Nate and Narav came up to Epic Seattle and like, hey, we've got this cool Crystal Cove prototype. It can track your position now, so we want something that shows off that you can move your head around in VR finally. So what we decided to do was take the large environment of the Elemental demo and then put something small but full of life and compelling that would make people want to naturally kind of lean over and get their face in there. So it was basically like a little tower defense thing where you massacred dwarves running around this little tabletop game with the gigantic meters-tall lava knights sitting in front of you. And the way we realized that we had success with this was there was a press video of somebody doing the demo. They leaned forward and smacked their head against the desk, and we're like, success! We got them to move their head. The other thing, I'll just blow through this really quick because it's not super interesting, but it's kind of cool. With the camera, we had to basically handle the case where the tracking camera lost sight of the player. So, you know, if you cover up your DK2 and it can't positional track, you still have rotation, but we wanted to encourage people to get back into the camera, thrust them. So the first idea we had was just throwing an arrow on there because arrows are simple, everybody understands them. When you go out of the tracking range, the arrow says, hey, move back this way and you'll be back in. And it works, but it didn't really fit with the theme of the world. You know, you had a big giant arrow in this cool fantasy setting and it really drew away from it. So the second idea we had was to actually draw the camera frustum in the world, and then when you got close to it, make it visible so that people had something up close to their face that they wanted to move away from. And again, that worked, but it's kind of intrusive to the world. So in this image, if you can't tell what's going on, basically that's the camera frustum, and the player's moving to the right, and we start drawing it up in their face to try to get them to move away. And again, it worked, but it didn't look super cool. So we decided to do a little more reductive design and just desaturate the scene, make it black and white when they lost tracking. And it was actually really cool because people noticed that something changed and was different, and that caused them to, they would move over and then like, oh, something's different, and sit back up, and they would automatically be back into the frustum volume, but it didn't pop them out of the world like the other kind of artificial constructs we had come. So I guess the lesson here was that, you know, you don't have to do something super complicated. You know, try reductive design occasionally, and sometimes you luck into something that works out well. Last thing was ambient motion. We, from the snow falling in the last demo, we thought it would be really cool to have a bunch of like dust particles floating in the air around people, but we noticed that the dust particles had a little bit of animation so that they were kind of swimming a little bit, and even if people weren't moving, they felt like they were moving on a boat, so it really made a lot of people that were sensitive very sick. So we ended up keeping the dust motes in there, but we turned down the transparency on them and then reduced the animation so that they were just kind of an ambient field as opposed to something that was swimming around. And then the last demo that we'll kind of talk about is Couch Nights, which was kind of a shared virtual experience. I'll blow through this super quick, but there was three main things we're going for here. We wanted to make player motion map to an in-game avatar, so when you moved around in the chair, the avatar, you had an actual body in the world, it would move around, so when you lean forward, it leaned forward, all that sort of stuff.
One of the funniest things I realized is that people would always look down and go, huh, my pants aren't that color.
Yeah, there's a lot of weird, quirky things. We'll actually touch on that a little bit later. And the second design goal was we wanted to have multiple players in a shared space so that your body language was there. You could see yourself, but you could also see somebody else interacting with you in the same space. And then the last design constraint was one we added. In order to make it a more social experience, we wanted a super simple but compelling kind of competitive mini game in there. And Couch Nights didn't actually start out anything like Couch Nights, and again, because of time, I'll blow through this, but originally we tried to take Owen from our Samaritan demo and throw him in there. And it actually worked really well at first, but until you looked down and you noticed that your hands were dead and you weren't holding on to anything in the real world, but you looked down and your hands couldn't move, and it really freaks people out. You know, at least because they're sitting, the legs were in the right position, but having your arms out in front of them just really upset people for whatever reason. So how do we get around this? We said, hey, if we, you know, looking at their arms and serve them, let's put their hands behind their back, right? You know, and it actually
see where
worked,
this is
you know,
going.
out of sight, out of mind. So we're like, how do we fit this in the narrative? Of course, an interrogation scene, because who doesn't want to be interrogated, right? So we figured players will be bound and gagged in an interrogation room and work together to escape, because we thought that'd be cool. You know, they'd use body language, and it would force them to communicate with each other to there. And we told Nate and Brendan about that idea, and they just GTA 5 flashed through their heads. Like, we can't do that to people at GDC. So back to the drawing board. And one of the artists at Epic, Thomas Browett, was making this cool little Zelda-like game with these pretty compelling little cartoon characters. So we said, what if you were sitting in an apartment with somebody else and you had toys that had kind of come to life and started beating the shit out of each other? And we said, that sounds like a good idea to us. So we still had the arm problem, but fortunately now, because we're having a gameplay where we weren't just relying on the body motion, we said we can give these people a controller, and then we can put that controller in their arms. And so what they're doing in the video game world was the same as what they were doing in the real world. And that let the player's proprioception match up with the in-game visuals. And so awesome word alert, proprioception is basically your sense of where your body is, even without the visual field. So if you close your eyes, you can still tell where your arms are and touch them together and stuff. It's that internal sense, and we found it's very important to make that at least mostly match up with the visuals that you do in the game. So having him hold the controller was the key to that. Then the next thing is yeah, we're running way out of time. So body language, we mapped the player's motion to the avatar in there. And the funny little anecdote about this is the first time we tried a network game, I was in there with Nick Donaldson. I didn't know that it was actually working.
Our first test was the heads going.
Yeah, exactly like that. It was totally spazzing out. So by the time we got to the real test, I looked over at Nick Donaldson in there. I didn't think the avatar was working, and he gave me the, like, what's up, bro nod, and I looked back at him and I'm like, what's up?
We did that for the next 20 minutes.
I know, it was just so amazing. That was my welcome to VR moment, you know, shared sense of presence, and we ended up referring to it as the bro nod heard around the world. It's still one of my favorite moments from VR.
Yeah.
Another quick note was that the character we picked was a little bit of thuggin'. He had very meaty hands, skull rings, and tattoos, and it really made a lot of people feel odd, especially women, we noticed, because the hands were much bigger, and that really didn't match with their body image. Plus, a lot of women felt very uncomfortable being around such a kind of thug gangster person in VR, and they can't escape. So we found you have to be very sensitive to these sorts of issues that, you know, usually when you're in a game, you don't care, right? Because you're transplanted on an external character. But when it's you in there, those sorts of considerations are much, much more pronounced. This was another quick thing. We had a neutral facial expression on the guy, and we wanted to add a happy face and a sad face for when you're doing good and doing badly. We found that actually adding those expressions made the uncanny valley much, much worse, because when you had some facial expressions, people noticed that you didn't have facial expressions the rest of the time. So since we had no time to get more animators to make us facial expressions, we ended up yanking them out because we were creeping people out too much. Eye tracking was super duper important for this. We added 3 targets because usually when your eyes are looking straight ahead, that's another thing that really creeps people out, the uncanny valley. So we started saying you can look at the other player's character, your own character, and the other player himself in there. But the interesting thing about this is we had to tune it to within 1 or 2 degrees of when you're looking at him, when it swaps to the next target. Otherwise, you kind of have
way
this
worse
creepy,
when you have.
Yeah, creepy out of the side of your face, glaring at people. Another thing that it really just took. We were sitting, you know, across the country from each other in Skype and saying, all right, a little less, all right, a little more, a little more. And then because of all those issues, we found that the people actually bonded much more with the little night girl in there because she was more cartoony and more abstract, and people kind of supplanted emotion onto her. So the biggest rewards, bang for buck things we had were actually giving her simple facial animations, smiles, and a little victory dance. Those became the crowd favorite. And one thing, I wish I could find the video, but it doesn't seem to exist online anymore, is this paper called Exploring the Effect of Abstract Motion in Social Human Interactions, where these researchers basically took a 2x4 and actuated it so it can move around, and then they put people in there and said, just interact with the 2x4. And they found, even with the simple motion of just a stick waving around, people actually, it was 38 out of the 40 people they tested actually felt that the stick was angry at them, or the stick was happy with them, or the stick was their friend. So it's really not about how high fidelity you can make the visuals all the time. It's about making the kind of anima for there. You know, you add animations, you add character, you add personality on top of these abstract objects, and it really sells. Showdown, he already talked about, so I'm just going to blow through this since we're out of time. We need your feedback. Let us know what you thought of it, what worked, what didn't work. And finally, just personal plugs for this, how we see VR at Epic. We kind of see it as the next progression of a narrative medium. You know, you can kind of look through history, and we've gone through oral storytelling, written storytelling, plays, film, games, and now virtual reality. And each one kind of adds one element that we can control on top of the previous ones to make, you know, a new way of telling a narrative. And we really feel that the addition of presence on top of games is what makes VR super special and very unique. So we hope to kind of further explore this in the future with our demos, and we're on the cusp of a new medium. And, you know, succeeding and failing, either way we go, we hope that everybody here shares the knowledge as much as possible. We try to be as open as possible with our development, because we're all learning and we all want to see the common goal of VR succeeding and achieving legitimacy. And with that, we are only slightly late and done. Thank you very much. Again, thank you to Artem back there. He's awesome. Couldn't do it without him. Thanks for Nick Donaldson.